Hello. Today we are going to continue with our series of videos. In this video, I'm going to talk about the RECP, the Resolved Stellar Population concept, and that are the library templates or templates that we use to analyze data from the LVM using the LVMDAP. In a sense, an RECP library is a set of templates of stellar spectra, but instead of being spectral characteristics of particular physical properties like temperature, gravity, abundance, metallicity, each RCP spectra correspond to a group of stellar spectra that are indistinguishable in the Welland range that we analyze. So they have the same kind of spectra or very similar spectra within a certain range of degree of freedom that is defined when we define the clustering. And it does not correspond to a single value in the physical parameter, but in a probability distribution function in the space of physical parameters. Then, in this way, when we decompose the spectra using RECPs, we should not assign or tag the fitted spectra with a single value of these physical parameters, but with the propagation of these PDFs. So, in a sense, this is a plot that I have taken from the article where we present the results of the DAP, and when we describe the DAP. And this is a particular RCP template that contains 108 spectra. And in here, I represent just a few of them. This is the ID here is just the numbering in the RSS in the row of this RSS file. And what I'm showing here is the spectra, and in black, and in orange is the spectra that have been contributed, the range of spectra that has been contributed to generate this particular spectra in the clustering process. So, in other words, this range of values of spectra is the degeneracy that is propagated through the RCCPs, and this degeneracy is transformed to a PDF in the physical in the space of physical properties. So we have distributed different RCPs. I will share the link later. Created with a clustering process, and the one I'm showing here. Let's see where I read the file. Just a second. Maybe I should enlarge this. I don't know if it's going to be enlarged. Yeah, to visualize it. Okay, let's read the file. It's just here, Bob. There's a lot of test plots in here. I will share the notebook. It's the notebook that I use to generate these templates. So in here, I'm reading. I will show you what it is. This is an original library used for generating these RCCPs. Just grouped by physical properties. It's the original library is the master library that was tagged using the tagging that was made by Alfredo Mejia Narvaez in this. You can download this tagging and the full library using the COSA code. It contains of the order of 30,000 stars. I will show you later how we clean those spectra fulfill the requirements that we need for the clustering. Okay. And this is just a simple, it's one of these cleanings that contains 14,000 stellar spectra, and this is used just for comparison in this notebook. The library is read where is read the library? So in here. Uh, okay, so this is before. This is just doing the minimum clustering, and the library contains 1,000. 100 to 235 stellar spectra. I will show you how this is generated. Okay. And this file, the shape of this file, it should be, no, that's not in here. It's in here. Sorry. Yeah. Okay, this is sorry, this is the RCP file that has been already clustered. It's the one that I show you later on, and it contains 108 RCCPs. This is what we distribute. So it's the master stellar library cluster to create a subsample of 108 spectra. In each file, in each of these files, and I will show you how we generate them, we contain all these extensions. The first extension is an RC, row stack spectra, containing the 108 spectra. Yeah, that's how we generate them. I will explain now. The second is a table with the parameters, the average parameters. So, although we have a PDF associated, we also have an average value that is the average across the PDF of the different parameters, the temperature, the gravity, and so on, and the associated percentiles that correspond to the errors. Then we have an error map. So this will be the range of it's like a standard deviation, and it's not the error of the mean, it's the standard deviation of the different spectra that has been included to create this clustering. So it will it will correspond to how generated is this spectra corresponding to these parameters. And then there is a table of the original parameters. And as you can see, it's much larger because these 108 cluster RCPs are extracted from a subsample of 1,235 stars from the master library that I will explain you how is generated. And in here, for each of these 108, you can recover the original values, physical values of each of the stars that enter into the clustering. These 1,000, around 1,000 stars they have been created clustering in the physical in the space of physical parameters, in the space of temperature, gravity, and abundance and metallicity. And this other clustering, the 108, has been clustered in the space of the observed parameters, so in the spectra. So I will get back to that because I'm going to describe all the process. But so far, that table basically recovers the original distribution, and there is an additional column that assigned to which cluster the star has entered. Just in case that you want to trace back to the original values. And then we have a set of projected PDF. So this is the PDF projected in the space of temperature and gravity. This is the PDF projected in temperature and metallicity. And so in the different projections that you can generate with the 4 parameters. These PDFs have the shape of an image, so it's a sample in the 100 by 100 in a certain step that is stored in the word coordinate system of these PDFs. And as you can see, there is a PDF per RECP, so that we have at the end a cube. So the first slice in the cube correspond to the first RCCP in the row stack spectrum here, the second to the second, the third to the third, and so on. So you can you can recover the physical parameters either multiplying, when you make a decomposition, multiply the parameters in this table by the coefficients that are normalized to 1, and you have a luminosity weighted value of average value of the parameter, or you can recover the PDF of the decomposition, multiplying each PDF in here by this coefficient, and then co-adding that PDF, and then you will have a single PDF. Okay, so this is the way we operate. And just I think here we have an example of how this works. This is a fitting that we have made in the center of Orion, and it's already created this average values that correspond to averaging the coefficient, multiplying the coefficient by the parameters in here and making the average. But we have also the coefficients, and these coefficients are the weights of the decomposition. Um, um, okay, so um, coming back. So here it reads the coefficients. Okay. Um, Now, of course, you need to use exactly the same cluster of RCCPs that you have used for the analysis when you want to reproduce the PDF reading the coefficients. Because if you are decomposing with 108 and then you are exploring with a cluster of 342, then there will be a mismatch in the number of coefficients and the number of PDFs in these extensions, and then it will not work, obviously. That's another example. Instead of having 108, you have 342. Then, of course, the RCC, the raw stack spectra contains 342 spectra. The errors contain 242 spectra. And the PDFs cubes contains 342 slides. Well, anyway, so once you have read these coefficients, you can generate the PDF. In here, for instance, I'm going to read the extension of the PDF cube of temperature versus gravity. And what it's doing here, it's multiplying somewhere the map P, okay, it's here. It's multiplying, making the average of the PDF cube weighted by the coefficients in the decomposition. So that's basically deriving the average PDF. And what you get is this distribution here. So what is plotting here in black is in contours is the PDF of the complete cluster. So the complete cluster it's covered this range of parameters in tomato red. Is that it's plotting the actually yes, is the tomato color. The PDF of the decomposition of the stellar content for this particular example that correspond to one certain particular analysis that I don't remember exactly which point it was, but it's irrelevant because it's not what we wanted to show in here. So to take off or to take away, you need to know that the RCP is a library that contains a set of templates that are stellar templates these stellar templates that do not have associated a particular physical property, but a PDF. The way that these RCPs are constructed are basically clustering the spectra of the stellar library in the observed space, basically in the spectra. So it propagates the genesis through the PDFs. And prior to that, instead of using, and that's what I'm going to show you now, instead of using the full library, we group that library because libraries of stellar libraries, like for instance the master library contains 30,000 stars, and not all of them have the same signal to noise. Not all of them have the same quality. Some of them contains emission lines that because there are emission lines associated with the atmosphere of the stars too, in certain particular stars, and so on. And all this is clean. And prior to making the cluster in the observed space, we cluster in the physical space, so all the stars that have the same physical parameters are clustered together. So instead of having 30,000 spectra, the cluster in the observed space is made on a pre-cluster set of spectra that contains the one that contains 1,200 spectra for this particular set. And the RCPs have this format, and this is the format that is expected as input in the LVMDAP. So if you want to generate your own recipes, you need to generate this format. So that's what is the content and how this is generated. So then let's start from the beginning. We start with an stellar library, and that should be here in this one. Cluster plot here. So in this case, we start with the that's master, the one that we start master clustering. Okay. So we start with an stellar library. Let's see how this is created. There are many functions in here that are not relevant. In a certain moment, we start reading the original library as it was created by Mejia Narvaez. So the catalog, it's in here, and the file is master catalog, okay? If you want to use other Stellar library, you need to start reading another catalog, and most probably it will have a different format. So the input should be modified in this script in here. Let's see where we read that library. Master catalog. I think it's no master. Maybe no, that's already. This is one is already created. So this is reading. So it's not that one. Should be master library. Yeah, I don't know why. Yeah, I was looking in the wrong way, in the wrong notebook. So we start with master library. Okay. And we start reading master catalog. Well, due to memory restrictions, I took the original catalog that it should be here, and that's the original catalog. Okay, it's the complete catalog. And what I do is to split it in a bunch of 1,000 stars because of memory restrictions. Now that's That's not a limitation. If you have more memory in your computer, you don't need to do that. So this step in here is basically cutting the original catalog in bunch of 1,000 stars, but that's totally irrelevant. So the original catalog contains, I say 30,000, sorry, contains 20,000 stars, nearly 23,000 stars. And basically the format of this catalog is the raw stack spectra with the two nearly 23,000 stars, and in the RSS raw stack spectra format, and the catalog with the properties, temperature and gravity and so on, and uncertainties. Okay, so the first we do is to select a well range corresponding to, I think it was H delta, and mask all those stars that have any emission in H delta. See, H delta is not a particularly very strong line. But if we have H delta, obviously we'll have H gamma and H beta and H alpha. So if you mask in H delta, you are masking any possible contribution. And then I make a mask also in signal to noise. And this is a mask of signal to noise 5. But obviously you can do the max that you want. And I did the different tests. 5 was enough. I also mask in the flux intensity. So the combination of these two fluxes, these two cuts, because the signal to noise correspond to a certain Wellen range, and the flux, the normalized flux, correspond to the average flux that was normalized. So the combination of these two are a good compromise between the number of stars that are retained and the quality of the individual spectra. Obviously, this is a question of testing further and try an experiment on that. So when you do that, you end up with a sample of 19,000 stars, so it's quite a lot. So we have thrown away about 4,000 spectra. Well, once you have made that, well, that's irrelevant. There are some tests that I were doing comparing with a previous binning that was created by Alfredo, using different approach. Well, this is the distribution of these 19,000 stars in the log G. I mean, the temperature, gravity, and color is the average metallicity. These are just some plots of how the space of parameters are filled in this with these 19,000 stars. I made some test of what happened if you cut in different intensity levels, just to show that this is just for plotting. It's not that relevant. So when we have this library, what we do is to cluster to group all the stars that have the same physical parameters within a certain range of values. So this is just that's an interesting plot, is how it changed the gravity versus temperature distribution for different cuts in abundance. Just to see if for different abundance we already have the degeneracy, a non-complete coverage of the space of parameters for the other parameters. That's it's not relevant for this. It's interesting, but it's not relevant. So what I do afterwards is, okay, I estimate the average errors that are in the catalogs, that are provided for the Stellar library for the different quantities. And then I create bins of the size of of half of this error in more or less the half of this error in the different parameters. So for alpha enhancement, I create 200 bins and a jump of 0.15, and this is a fixed binning, so it's making these cuts of 0.15 index of abundance, 0.2 in index of metallicity, 0.03 index of temperature, and 0.3 index of index index of gravity. So I create these means, and once I create these means, then I go to the original spectra, and I group all those stars that enter in these different bins. So that's maybe there are more elegant ways of doing that, but basically, once you have the bins, you assign to each bin the stars that are within that bin, making this max. And when you have that, you obtain the average parameters of those stars that are in this location and the standard deviation. And for each bin, this create per se a PDF of the in the space of parameters, physical parameters, of each individual cluster that we create here in the space of physical parameters. And of course, we create the mean spectra and the standard deviation spectra of all the stars that enter in the same bin. So, and I think I have a plot here of how it looks like. Um, so that's this is the distribution of all the stars that enter in each cluster. Okay, and then you average these properties, and you obtain the average property of the cluster and the average spectra. Since they are stars with the same physical properties, obviously they have the same spectra. And so what we are doing in this process is, in a sense, increasing the signal to noise of the spectra associated with a set of physical parameters. So from the 19,000, with this cut in signal to noise and this range of sampling the space of physical parameters, we end up with a sample of 1,235 stars. These, we already have an RCP in here, and with a very good sampling of the space of parameters. But in here, we are not taking into account the degeneracies. The degeneracies are kept in here because we are making the clustering in the space of physical parameters. So it may be the case that two spectra that are located in here and in here, look very similar, and they correspond to very different stars. So the second clustering we do is that we glue all them together, and we generate a PDF that is basically could be bimodal, for instance. So the impossibility with the precision we are handling of distinguishing between stars that have the same spectra is propagated in the PDF, as I said you before. But we could try to fit with the LVMDAP using this template. I don't recommend that because that's computationally a big effort, but we could try. I mean, and actually, it will be a funny test to see what's the difference of using the full library. Going to a larger number of that, it's has not too much sense because you will sample below the typical errors. So that's not it's not relevant. You can try, but it's absurd. Well, absurd. It's not recommended. Let's be more soft in this claiming. So this is the distribution that we have of these 100 and 1200 stars. So, and this is in the space of, so this is the coverage that we have in the space of abundance versus metallicity. Okay. Yeah, so once we have that, now we can cluster. Well, that's I think that this script ends here. This is just making tests of different clusterings, but that's the script ends there. It generates this subset of spectra that have the same physical properties and has clean for emission lines and has clean for low signal to noise, and make a clustering in the range of in the space of physical parameters. So you go to the article. This was described in the cluster in the article. Now we have that catalog that is stored in here. Is the master library with a clustering of 1,000, 1,200 stars with a signal to noise of 5. We can use that as input for clustering in the space of observed parameters. So in the space of spectra. So we made the comparison here from the original master catalog target with Kocha, and the distributions are cover the same range of parameters, but they are slightly different because we have reduced the degeneracies, and so there are regimes where we have more stars than what are required. So the distribution in general are flatter with the new subsample that now for each location in the space of physical parameters, we have assigned one spectra, and in the original master catalog, this is normalized by the volume distribution of the stars. So basically, you may have thousands of stars in one bin, and this will be represented here as a peak that is not representing the distribution of parameters, but the distribution of stars. Anyway, so once we have made this, that's just again very simple comparisons like before of how the original clustering correspond to the sample we have. Then what we do, let's see if it's shown here. Okay, it should be somewhere. Well, these are tests, and here is the clustering. Okay, so the clustering is done basically based on the distance in the space of observed parameters between one spectra and other spectra. So that's cluster is already defined here. Let's see where is the clustering happening. That's cluster is already created. Sorry, what it was that? What it was that? That's just to generate the PDFs. So you need to make it here. Okay. So the function that do that, you can check that function later on, is this one, spectral clustering. Spectral clustering takes as input the number of clusters that you want to generate, the number of neighbors that enter into the clustering, and the affinity. And afterwards, it's create a cluster that is grouping the spectra and grouping the PDFs for each particular cluster. So that function, spectral clustering, spectral clustering. I don't know if it's in. I saw it in here. This has been taken from sklearn. So you can go in here. So it's not a function that I created. It's come on. it's using this routine. Okay. Um, and it was made but to basically doing what I mentioned, that taking the adjacent in the space of shared parameters, uh, take the ones that are more near, and based on and selecting the number of clusters, and group them, so and assign this clustering. So now that you have which clusters, which spectra correspond to a certain cluster, then you can create the PDF and the projections of the PDF in temperature and log and so on, based on the PDF that you have from the original 1200 stars, and multiply them by the grouping, putting together all those stars that correspond to the same cluster. Okay, and when you have that, you generate the map density, and this map density is what is stored in the extensions that you have seen before. So, and the spectra, the raw stack spectra, where they are. Well, this is the these are the PDFs basically. Um, uh, that obviously this is the abundance versus metallicity of the full sample, and when it was created, the spectra. That's this is just um, how it's distributed the original spectra. So it's actually, if you that's this thing, cluster now. Okay, so yeah, it's this is a mask. This is the basically the spectra 2D. It's a subset of the original spectra, correspond to the cluster number 35. And what you are plotting here is the mean spectra and the individual spectra that enter in that cluster. So this is just one example. And for all the full set is what I show you here. So in here is reading the original raw stack spectra with the 1200 stars, and making masks that correspond to the cluster 18, the cluster 48, the cluster 90, generating the average and the standard deviation. And this goes through all the clusters and making this average spectra and storing this average spectra. So at the end, this average spectra is and the standard deviation are stored in the output file that it's going to be shown here. That these are just some few tests. Uh, Here is where it's going through the clusters. Okay, selecting the cluster, creating the mean and the standard deviations. But instead, I'm also for the tables to create the PDFs, and also deriving the average parameters. And once you have that, this is the just plotting some examples. At the end, this is stored in a recipe file that it's written in here. So what we read in here is first the mean spectra, the table of parameters that has been defined before in this loop, the standard deviation that basically corresponds to the extension error, the original parameter of the original table that we have at the column of the number of clusters, the cluster ID that this spectra has been assigned, and the PDFs that correspond to the projection of the different the projection of in the different space of parameters. So this file is the one that was later on shown in here. I think it was in that one. You see? This is the average spectra, the average parameters, the standard deviation, the original parameters with another column that is the cluster and the different PDFs. So, in summary, we start with a Stellar library. We make some cleaning, removing. You can look for more problems in the spectra, defects, or whatever. You make the cleaning that you require in signal to noise, avoiding emission lines, or whatever you prefer. Once you have that, you group all the stars that have the same physical parameters within the errors. So you don't need to repeat the spectra that are equal, and you group them, making their average. So this way, all the spectra representing the same physical parameters increase the signal to noise. So we start from 22,000 stars. From the cleaning, we end up with 19,000. From the grouping or clustering in the physical parameters, we end up with 1,200. And then we make a clustering in the observed parameters, and we end up with the number that you define, that in this case were 108, but if you go to this clustering here, we created different, well, this is just the distribution of stars here in the clustering. This one have a different number of clusterings that is a number that you can define, and this is why in the RCPs that we distribute, they have different numbers. So I created a class just 4 spectra. Of course, this is totally degenerated. 12 is not that degenerated. 32, 70, 108, and 342. And as you can see, this is there are multiplicative factors, so one to the other. But it's like a factor 3 from one to the other. And if I go beyond that, I enter in the regime of the original sampling. There are 12 a number. There are 12,000. 1,200. So it's absurd to make another clustering. So you can fit with the original sample that is the original template that's not propagate degeneracies. So okay, so this is basically how the RCPs are generated. I'm going to upload all these scripts. So you can, if you have a different library, you have a theoretical library, whatever, and you want to generate your own RCPs, you can follow. I mean, you will need to modify some of these scripts, but you can follow this sequence, and you will end up with something that we can use for the LVMDAP, and it will be fun to test with different libraries. So just check the final format so it fits with what the LVM DAP requires. If not, the fitting is not going to work. Okay, that's all.